All right. Welcome, everyone. Thank you so much for joining us this morning for another Saturday morning science session with the MSU Science Festival. I'm Katherine Hagman. I'm joined by Roxanne Troon from the Science Festival as well. And this morning, we're also joined by Dr. Dean Lee from MSU's FRIB. Welcome.
Thank you.
Thanks so much for joining us. Before we begin your presentation, would you mind telling us a little bit about what you study, what your background is in, and a little bit about what we'll be talking about today?
Sure. So I came to FRIB, the Facility for Rare Isotope Beams, in 2017. Before that, I was a professor at North Carolina State University. And my area of research is in nuclear physics, nuclear theory. And so we do calculations of how protons and neutrons come together to form atomic nuclei. And a lot of this work involves understanding the spooky world of quantum mechanics. And so today's lecture is about quantum mechanics, hopefully at a level that everybody can understand.
Wonderful. All right. Well, if you're ready, we can go ahead and get started.
Sure. I will go ahead and share my screen. Hopefully that's working. Can people see that?
Yep, I would go ahead and put it into presentation mode and then.
Yeah, we're going now. Okay.
Yep, it's good.
Excellent. And feel free to type in a question if you have any, and I will stop periodically to allow you for Catherine to read the questions, and I'll try to answer them. All right, so I'll be talking about the quantum world of atomic nuclei. And this is work done by myself with a bunch of collaborators. And you'll see some of the names of my collaborators as we go through each topic. So let me just start off, though, telling you about the Facility for Rare Isotope Beams. So this is a $765 million facility at Michigan State University. That's a partnership with the Department of Energy, with the state of Michigan and Michigan State University. And what we're doing at FRIB is to make these exotic nuclei, nuclei that are difficult to make any other way. And we do this to understand a few different questions. One would be, how do we see, or how do we make all of these elements, these chemical elements that we see in our universe today? For example, from gold to platinum to maybe even more mundane elements like, well, like carbon and oxygen, but those we don't need FRIB for. But some of the other questions we want to understand are the limits of stability. How many protons and neutrons can come together and stick to form an atomic nucleus? And at what point do they fall apart? Some other questions would be to try to understand the fundamental forces of nature. And so FRIB will be making certain nuclei that allow you to probe these small effects that are hidden that you might not otherwise see, to look for new physics that we never knew was there. And then there's also applications of FRIB science to making nuclear isotopes for medical treatments as well as diagnostics. So my research group is involved in the theoretical side of FRIB science. And specifically, we try to start from scratch and explain what we see in these experiments that will be done at FRIB. And that, by the way, that will start happening in about 1.5 years from now, in 2022. And so what we do is my research group, we work to understand the nature and origins of matter, and we try to devise new approaches for calculating what's going on inside of the nucleus. So, but let me start off the lecture by just telling you about classical particles. So suppose you had a bunch of little pebbles, and there were 2 holes in a piece of wood, let's say, and you drop these pebbles, and every once in a while, the pebbles will actually go through one of the holes, and then it will land on the floor. Now, if you keep doing this over and over again, you'll start seeing that there are 2 holes in this sheet. And at some point, you get some sort of a distribution of pebbles that have gone to the other side. Okay. Now, you can ask, so this is what's called particle behavior or classical physics, and that's not really mysterious to you because you've seen this before. However, you can also ask the question, what happens if you shine light through a sheet that has two holes? Then you get a much different behavior because light has a wave-like property. So you can think of light, or you can think of maybe water waves coming to a shoreline, and you have these wave fronts going steadily, evenly spaced, coming through. And then once it hits the sheet, you see that there will be 2 point sources of light, and they will curve the wave fronts in such a fashion. And as these wave fronts propel further, you'll see that they overlap with each other, and that forms what's called an interference pattern. And this is probably familiar to you when you throw 2 pebbles into the surface of a pond, you'll see these ripples, and you'll see these intersecting circular wave fronts, and they form these interference patterns. Now, so if you have light that then shines through the sheet with these 2 holes, and then you ask, what is the pattern that's seen on a screen far away? What you see is that these interference, where the wavefronts overlap, you get the strongest amount of light being focused onto this sheet, onto this screen at the far end. And then you'll see another maximum here, another maximum here, and so on. So this is what we call an interference pattern. And so it looks something like this. You see these wiggles. There's a big central maximum, but then there are side maxima that you see. And so if you were to analyze what was going on here, you could say there's a probability distribution, how likely it is to see light particles at one position or another. And you could say there's a 30% probability here at the center, and then there's a 20% probability here on the side bands next to the center. And then over here on the edges, there's maybe a 15% probability. Okay, let me pause just for a moment and ask if there are any questions already at this point.
There was just one question that came in early that they wanted to know the difference between a neutron and a proton.
Okay, we actually haven't. Okay, yes, I did mention neutron and proton in the beginning. So a proton is a particle. It's one of these nuclear particles that has a positive charge. So the simplest way I can explain a proton is if you have hydrogen. So hydrogen is the simplest chemical element, and hydrogen has a proton which is positively charged and has an electron that orbits around it. And so that's what constitutes a hydrogen atom. Okay, so the proton is that positively charged thing in the center. Now, a neutron is very similar to a proton, but it does not have an electric charge. It's neutral, and that's why it's called a neutron, neutral for neutron. But it has a mass that's very similar to that of a proton. And so what the proton and neutron can do is that they can stick together and they can form bigger nuclei. So for example, if I have a neutron and I stick it to a proton, I can form what's called a deuterium atom. So that would be the center of a deuterium atom, or what's called a deuteron. But I can add more protons and neutrons and form then bigger nuclei from that. Thank you for that question. So I'll carry on now. So this probability distribution is what you expect to see with quantum particles. By quantum particles, I mean microscopic particles. So in the microscopic world, lots of spooky things happen, like the fact that particles behave like waves and waves behave like particles. And here is an experiment. So this is a slide from Hitachi Global, what's called the single electron double slit experiment. So an electron is a negatively charged particle that, as I mentioned, orbits around the nucleus. But the electrons are used for electrical devices of all sorts. So hopefully that's a familiar object to you. Now, what's shown here in the slide is essentially an electron gun, something that is emitting electrons by heating up the source. And what you have in the middle here is a charged filament. So what happens is that the electron has to go one way or the other around this filament. It can't go through the filament. And so then there's a small hole here, and the electron has to pass this hole, and then it's recorded in this electron detector. All right. The point is that this is essentially a double slit experiment, just like we had before, in that we have two possible paths for the electron, to the left or to the right. And what's kind of unusual about this is we're only doing one electron every 10 seconds. We're shooting one electron, then we're shooting another one. So you would expect that this electron is behaving like a particle, so that you would see maybe some simple lump distribution of the electrons that you detect. But that's actually not what you see. What you see in the beginning, you don't see anything spectacular. You just see a bunch of random dots. And then you have some more dots. Still seems kind of random. But then you start seeing structures forming as you get more and more repetitions of this experiment. And eventually, when you have enough data, you see these ripples that are these interference patterns. So what's going on here is not that the electrons are interacting with each other, because each electron is being shot at individually, one at a time every 10 seconds. So what's really going on here is that the electron is interfering with itself. It's propagating through like a wave, like light, and it's going through the left and through the right. And then they recombine to form an interference pattern at the detector. And that to me is really quite dramatic, that a single particle can have this interference with itself. So let me maybe pause and ask if there are any questions that may have come.
No, not right now. I think we're good to go.
Okay. If you do have a question, go ahead and type away. There's a little bit of a delay, so it might take us a few moments before we see your question. Okay, so let me now talk about a free particle. So by free particle, I mean just a particle that's allowed to do whatever it wants. And so what a free particle does is it just moves in a straight line. So a particle will have a mass, m. It will have a velocity, or let's say the magnitude of the velocity that we call a speed, v. Okay. Then the momentum of a particle is the mass times the velocity, okay, m times v. Now, the kinetic energy of this particle, the formula for that is not too much more complicated. It's 1/2 m times the speed squared, or the velocity squared. Okay. Now, if I were to take this formula for p and square it, I would get m squared and v squared multiplied together. That's almost what I need for the formula for the kinetic energy. But what I need is a factor of 1/2. And then I need to get rid of this extra m that I get when squaring m. So the formula for the energy, the kinetic energy, is p squared over 2m. So it's just proportional to the square of the momentum. That's just the fact that I need for some of these plots that I'll be showing. So if I have a free particle, it has some momentum. It's moving in a straight line with some speed or some velocity. And the momentum is m times v. And the energy, the kinetic energy, is p squared divided by twice the mass. Okay. Now, so what does this look like? If I plot the kinetic energy versus the momentum, or the magnitude of the momentum, it's p squared over 2m. So it has this, what's called a parabola, or parabolic shape, this squared behavior like this. Okay. Now, perhaps I'll just pause for another moment and ask if there are any questions, because we went through just some formulas and there might be some questions on that. You're good?
I haven't seen any come in. I think we're good.
Okay, all right, very good. So that's all the formulas we'll have for this talk. So if you're not a big fan of formulas, you're all set for that. So now what I'm going to do is I'm going to talk to you about the different types of particles that exist in the universe. Okay, so but first of all, let's just consider what happens with one particle. So with one particle, it doesn't matter what kind of particle it is. Let's put this particle in the box. Let's close up the box. And then what we're going to do is we're going to cool down the system. So imagine putting this in a refrigerator of some sort, starting off at a high temperature. So the particle maybe has some momentum to it. And then we're going to cool down the system, decrease the temperature. And what will happen is that the energy of this particle will tend to decrease. It's just more likely to have a lower energy at lower temperature. That's just how temperature works. Now, if I reduce the temperature all the way down to 0, then what will happen is we will only have a particle at 0 energy, and so therefore 0 momentum. Okay. Now, let me tell you that there are two kinds of particles in our universe. One kind has a word is what's called a boson, and that's what we're going to talk about first. A boson is a particle. Okay, so there's something that's what's called spin. That's how much something spins around. And it turns out that in quantum mechanics, the amount of spin that a particle can have cannot be an arbitrary number, but it can either be an integer number or it can be half an integer number, like 1/2 or 1.5 or 2.5. Okay, and the bosons are the particles that have an integer amount of spin. Okay, so 0, 1, or 2. Whereas the other kind of particle is called a fermion, and that has the half, like 1/2, 1.5, 2.5. So what we're going to consider now is when we have 6 identical bosons, these particles with spin 0, 1, or 2, and we put them in a box. So we put the 6 bosons in a box, and we close up the box. And then now we're going to, again, turn down the temperature. So at a high temperature, they start off with some distribution, some random distribution of momentum and energy. But then as we decrease the temperature, they go down in energy. Okay. And then if we go all the way to 0 temperature, they all have 0 momentum, 0 energy. So these bosons, these particles called bosons, are gregarious, or they're social particles. They like to be on top of each other, which is kind of the opposite of what we need these days with social distancing. They like to occupy the same space, the same quantum state. And what's neat about this is that when bosons do this at low temperatures, they start behaving in very, very peculiar, weird ways. In fact, because they have the same quantum state, they cannot interfere, they cannot collide with each other. They just essentially just don't really pay attention to, they don't really, they're not complaining about the other particles that are occupying the same space. And so as a result, you get things like what's called superfluid or persistent flow. You can have a superfluid of these bosons just going around in a circle over and over and over without stopping. And you can also, with a superfluid, have some really spectacular behaviors, like you have a superfluid in a container. It can then adhere to the wall of the container, and then it can actually climb up over the edge of the container and leak out that way, this wall climbing effect. So it's kind of a macroscopic or large-scale manifestation or phenomenon that you see showing the quantum behavior of these bosons. Let me pause and ask if there are any questions so far.
Not so far. It's been pretty quiet on the question front. So
Okay.
again, if the people out there listening have any questions, write them in our comment section. Thanks.
Okay, thank you.
Could you go back and re-explain what is a superfluid?
Okay, a superfluid is basically when you have something like this, where you have a bunch of bosons, they all occupy the same state at low temperature. They don't collide with each other. They sort of just they essentially do the same thing because they, for all intents and purposes, think they're the same particle. And so if one moves, they all move together. And so they essentially flow without any resistance to flow. Yeah, that's what a superfluid is.
Okay, thank you.
Okay, all right. And there's a connection to something called a superconductor, where you have the flow of pairs of electrons that flows through a wire, and that's very similar to a superfluid. Okay. Now, let me talk about the other kind of particles, the fermions. So the fermions are the particles that have half a spin or 1.5 spins, okay? And they behave quite differently. So let's suppose we have 6 fermions that we put into a box. We close the box, and then we turn down the temperature. So we start off with some particles. So because these particles have spin, I put these little arrows to denote that they are all pointing in the same direction for their spins. And we cool down the system and they go to lower energies, lower momenta. But what happens with fermions is they are antisocial. They are socially distancing from each other. They cannot occupy the same space. And so as a result, there's a minimum energy sort of configuration that they can occupy at 0 temperature. You can't go to lower energies than that. So these fermions obey what's called the exclusion principle. It's named after somebody named Pauli. And so it's called the Pauli exclusion principle, that two identical fermions cannot have the same properties. So that's why they're spaced apart like this, so that they cannot occupy the same quantum state. All right. There's actually a name for this phenomenon. So this is what's called a Fermi liquid. So this system behaves much like a liquid. The particles are sort of spaced out from each other. And there is then a maximum value for the momentum, and that's what's called the Fermi momentum. By the way, Fermi is for Enrico Fermi, another physicist who this is named after. And then there's a maximum energy, and that's what's called the Fermi energy. Okay, so now these fermions are what describe the neutrons and protons that we've been talking about. And so so now I'm going to transition to talk to you about what the research I'm doing is all about. And maybe I can pause again to ask if there are any questions.
No, not
Very
right
good.
now. Thanks.
Okay. All right. So the work that I do is I take these protons and neutrons. So here are the protons and here are the neutrons, and they interact by the exchange of particles. So for example, something called a pion, which we won't spend much time talking about them. But these are bosons that are very light that get exchanged between protons and neutrons. But what I do in my research group is we imagine that space is divided up into a lattice, so essentially a grid, so that we can put this onto a computer, in fact, a supercomputer that I'll show you in a moment. And we take a lattice spacing that's very small enough to be able to describe the atomic nuclei. And we then put these particles on the lattice, and we put them onto supercomputers. So here's Summit, the largest, most powerful supercomputer in the world. That's at Oak Ridge National Laboratory that our research group does calculations on, as well as this computer called Joules, which is in Germany, which is one of the largest computers in the world as well. And we do these simulations. And with these simulations, we're allowed to figure out how these fermions, so we have the proton, which can have a spin up or a spin down, or we can have a neutron that's a spin up or a spin down. And we try to figure out how they arrange themselves into atomic nucleus. And so what I'm showing you here is oops, sorry, I didn't mean to go ahead. This is auction 16, okay? And what we're doing now is we're trying to compare our simulations with what's seen in the laboratory to see how well we can predict the properties of these nuclei, including these very exotic nuclei that we want to study at the facility for rare isotope beams. Okay. Now, let me go on. So one of the papers we did recently was to look at nuclear binding. What we did was we had some forces that we used for our interactions in our supercomputer simulation. And we played around with the forces that we used. And we found that we could actually make something kind of weird happen. In fact, we induce what's called a phase transition. A phase transition is like something goes from a liquid to a solid. It changes its phase. But what we found here was not a phase transition in temperature. This was actually a phase transition that happened as we changed the nuclear forces. And so what we were able to do by accident, completely by accident, was to make this nice nucleus, this nuclear liquid that we all see, And we were able to actually accidentally, by changing some parameter of the nuclear force, make it so that only 4 nucleons could stick together. Essentially, this was the largest nucleus we could build had only 4 particles, which is completely different from nature. In nature, you can get several hundred particles to stick together. But in this accident, we were able to make it so that only 4 particles could come together. Okay, let me pause and ask if there are any questions here.
I guess a question would be, how do you change the nuclear force?
Yeah.
What do you do to change it?
Yeah, so the nice thing about being a theorist is everything we put into our calculations, we can put in into the equations. So essentially, we can make the interaction between a proton and neutron slightly different. And that's essentially what we did. We made some detail of the interaction a little bit different in a way that we thought would not matter, but actually ended up having a tremendous impact. Now, I should mention, if I was an experimentalist, the idea that I would change the nuclear force would be sort of bizarre, because that's not something you can do in nature. That's just given to you. But as a theorist, you can take the forces you see in nature, or describes what's in nature, and make some small change to those forces, and then ask how is the universe different. Okay, so now the next topic we'll talk about is something. So the paper has a very complicated name, so I won't even read it here. But let me describe what the idea was of this paper. So let me just focus on this picture here. So there's something that's called the quantum mechanical wave function, just what's called the wave function. And it describes the system. It describes the quantum system that you have, like a nucleus. Everything you want to know about that nucleus is contained in this quantum wave function. And usually we use this symbol psi for the wave function. And what this research project was all about was, again, suppose we change some property of the nuclear force. So you can imagine changing maybe how strong the attraction is between the protons and the neutrons. And then you can imagine, as I change that nuclear force, the wave function then will be changing. So I can imagine then having like a road where I change the parameter, and as I change the parameter, the wave function changes. And let's say over here is maybe some nucleus with the value of the parameter that I really care about, where I want to describe what's going on. And in this research, what we did was we found that we could actually predict what would happen further along down the road just by studying very carefully what happened at the beginning of the road. If you had enough sort of precise measurements of what's going on in the beginning of the road, and if the road is smooth, that's saying that you could actually predict where you end up at the end. That's what the paper was about. What's called continuation. We call this technique is called continuation. Okay, let me pause and ask if there are any questions up to here.
No, I think we're good.
Okay, then I'm going to talk about my final topic, which is on quantum computing. So all the stuff I mentioned is about the spooky world of quantum mechanics and all the things we're trying to describe in the quantum realm. But you can actually take things from the other side, and you can try to build a computer using the spooky world of quantum mechanics from the beginning. Okay, and so this is not something that's you can buy a quantum computer today, but there's a lot of research now to try to build these devices. And so you see here what's called the company is IBM-Q, so the quantum computing division of IBM. And this is an actual quantum computer that they're making. And so let me tell you a little bit about how the quantum computer works. So for a classical computer, or the typical computer that you know about, you have what are called logical bits or classical bits, 0 or 1. 0 means no, and 1 means yes. And so what a computer does, essentially there's a bunch of yes and no questions. And with each yes and no questions, you have a fork in the road. If you say yes, you go one way. If you say no, you go another way. And then at each step, you ask another yes and no question. And then by making these logical, what are called gates, or these forks in the road, you can then build a computer. Now, the idea of a quantum computer is to do the same thing with these wave functions that can be 0 or 1, but in quantum mechanics, you can actually have a combination of both. So it's not just 0 or 1, but it can be any combination of 0 and 1. So for example, 0 plus 1 added together. There's a divided by square root of 2 just to make the normalization right, but that's not that important for this discussion. So because we have a much larger set of possibilities for the qubit, it turns out that we can handle much larger, more information, and we can, in principle, do calculations of much larger systems with a quantum computer. But the challenge is to be in control of the noise of a quantum computer so that you can do these calculations without having garbage at the end. So that's the main challenge these days. So the work that my research group has been involved in is in something called the projected cooling algorithm, which is a way to do a calculation to make a quantum wave function on a quantum computer. And the essential idea is to have our quantum system that we're trying to simulate, and we put it inside of a large box, what I call a reservoir. And this reservoir, think of it as like a very cold cooling pan, but very large, that starts out very cold. And what happens is that the system then will dump heat into the reservoir, thereby cooling the system. And so then the system will then drop down to its lowest possible temperature and go into its lowest energy configuration. And that's how we simulate the system in its ground configuration or its lowest energy configuration. That's how we do it. And so here's an example of how this actually works in a real application. We have some wave function that's a function of 2 variables, and it looks like some sort of landscape like this. And then with this projected cooling algorithm, we wait long enough time and we end up getting something that looks very, very similar to the exact wave function that we're trying to describe. Okay. Now, let me pause and ask if there are any questions.
No.
We're good? Okay.
I have a couple questions, actually.
Sure.
Could you talk about some of the uses of these quantum computers?
Yeah, so some of the uses that people want to do, for example, one calculation that people would want to do is to do some problems that are just extremely hard to do with a classical computer. For example, there is an example of what's called the traveling salesman problem, where you have, let's say we have 20 different cities that we want to, that a salesman wants to go to, with certain distances between the cities. And you want to then minimize the amount of traveling that's needed to reach all 20 cities. Now, the problem is that on a classical computer, you have to go through all of the possible arrangements of 20 cities in a row. So that's an extremely large number. And so it's a very, very hard calculation, essentially undoable if the number of cities is too large. Now, a quantum computer is, because it can make a linear combination or superposition of all possible things all at the same time, it can actually do this search over all possible paths of the traveling salesman, and it can do this in much, much faster time in principle. So there is the possibility that it can do these really, really complicated, what are called combinatorially hard problems, because there's many ways of making these combinations. So that's a lot of the allure of quantum computing, to do these problems. Now, I have to admit, myself, I'm not interested in those problems. A lot of business applications are interested in these problems for optimization for business. But in my case, I'm interested in being able to simulate very complicated systems like a atomic nucleus. If I were to collide 2 nuclei together, and all sorts of, at a high energy, and all sorts of things can happen. There is no classical computer that can really describe this process. Even though we can do it in an experiment, to get a classical computer to do this is very difficult. And this is the sort of thing that a quantum computer in principle can do. That's a great question.
Thank you.
Okay, so let me now just wrap up and tell you, for those high school students in the audience, or those of you who are younger, what are the relevant classes that you might want to take to doing this research. And so the first one you might have guessed is physics. That's where you learn things like quantum mechanics. But in order to understand the physics, you need to have a grounding in mathematics to understand all the mathematics that's underlying the quantum mechanics. In order to do these simulations that we do, we need to have some expertise in computer science to write these computer codes. But then also to be able to explain to everybody what we're talking about, we have to write papers. And so then some background in scientific writing is, of course, very, very important. So let me just wrap up and ask again if there are any questions. And this is just a picture of people waiting for a tour of FRIB. I know with the virus pandemic, people are not able to do these tours now, but hopefully sometime in the future, you'll have the chance to do so. Thank you very much for your attention.
Thank you, Dr. Lee. I did have a question. You talked about the computer systems offsite. Does MSU have any of these computer systems that you work with? Are they going to be part of FRIB or?
Yeah, it's not part of FRIB, but we have a high performance computing center that's very good at Michigan State. It's for a university computing system. It's really quite top notch, but it's not anywhere near these big supercomputers at the supercomputing centers that we use. So what we do is we develop our codes, we test them in the MSU cluster, the computing cluster, and then once we know that they're working and we know we have some production calculation to do, then we send off the big jobs to this supercomputer.
Will there be any, I guess, practical applications, like say 15 years out, will we no longer have these laptop PCs? We'll all have a quantum mechanics computer at our fingertips?
At 15 years seems unlikely. There still needs to be, I mentioned this problem of noise. So the problem with this, so a classical computer is relatively noise tolerant because you either have a 0 or a 1. And in order for a 1 to flip to 0, right? So there's something that's called error correction that one can do on a classical computer, and essentially you can have repetition. You can have 3 classical bits that do the same thing, and if you know that this classical bit should be in the 1 position, then you'll have 3 bits in the 1 position. But let's suppose that there's some noise and one of the bits switched over to 0. Okay, so but if you look at these 3 bits, you can still figure out that probably with a high likelihood this was supposed to be a 1 because there's a majority, there's 2 1s and there's 1 0. And by majority rule, you can essentially flip this back to a 1. And this is what's called error correction. All right. Now, we don't have a good, in principle we do, but we don't have a practical error correction code for quantum computers to do this, simply because of the fact that the quantum qubit is much more complicated, and sort of flipping things back to what they should be is much more difficult.
And we had a comment from Claude. He said he's just imagining a quantum smartphone. It sounds whack, but really sick too.
Yeah. Yeah, I agree. But once we figure out the noise problem, and it's a non-trivial question how far away that is to be able to make robust quantum devices. But once we do that, then the quantum computers will be able to solve certain problems faster than a classical computer for sure. And the nice thing is that you can meld a quantum computer with a classical computer so that you can have them working in tandem with each other. And so as a result, you could have something very, very fast in principle.
And go ahead, Catherine.
For computer programmers, do you see this changing the programming worlds in the future?
Yeah. Programming on a quantum computer is completely different from a classical computer. It's very much quantum mechanics when you're programming in a quantum computer. You have to think about what is this wave function that I have at any given time propagating through. When you do classical computing, you're simply thinking in terms of loops and if then statements and stuff like that. It's really quite different.
So do you see this as being like the new future for programmers eventually?
Yeah, so there's already now a lot of excitement in quantum computing, even though, as I said, it's not quite ready for prime time yet. It's not really a mature thing, but there are some companies that are making devices that actually solve real problems. Like D-Wave is a company in California that actually can solve certain problems. Um, uh, so it's real. It really does things, and there's lots of excitement, and there's lots of money, and there are lots of young talent going into this field. This I know because I know a lot of young students, including in my group, that are interested in this.
Mm-hmm.
And then Claude wanted to know, would it be like a dual boot or another working type altogether?
So it's, well, he's imagining a real quantum computer with a classical computer. Whether you can dual boot to quantum to classical, that would be pretty cool. I would imagine that because that's so far away, I'm just completely guessing. The quantum computers really require some special like low temperature systems and some special care. So I would imagine it would probably be its own separate device that maybe would interface with the classical computer. I wouldn't imagine that they would be sort of occupying the same box together. It would be hard to imagine that.
And then just going back way back to when you were talking about the nucleus of things.
Mm-hmm.
So our artist's rendition of what a nucleus looks like, will that change based on what the work you're doing with seeing the forces affect the nucleus differently?
Yeah. So the work I do is more in the details. So here's like maybe an artist's rendition of the nucleus here, and we know that's pretty. Well, okay, this is an artist's rendition, but the experimentalists do things like do electron scattering experiments where they scatter an electron off the nucleus, and they can get a profile of where the electric charges are in the nucleus, and we have a pretty good sense of the shape, the size of the nucleus. There are other ways to also get information about whether it's deformed, whether it's spherical or some other shape. But those sort of basic sort of gross properties we're pretty sure about from the experimentalists. But the work I do very often is to try to figure out the fine details of something going on. For example, one can describe how the electrons in a metal behaves very, very simply in terms of what's called band theory, just simple non-interacting electrons sort of just shooting across, not interacting with each other. However, so essentially 90% of electricity or electrical conduction can be explained in terms of this simple band theory picture. But if you want to understand some subtle phenomenon like superconductivity, that requires understanding the fine details, and in fact, understanding the quantum mechanics of these electrons. And so what happens in superconductivity is that you actually have a pair of electrons. So remember I said electrons are fermions, but if you take two fermions and put them together, they form a boson, okay? So what happens in superconductivity is you have one upspin electron and let's say one downspin electron, they pair up, okay? They pair up to form what's called a Cooper pair. And that boson now behaves like it's in a superfluid, and it conducts and it flows through. So to understand that detail, you have to really understand what's going on at the deep quantum level. So my contribution, what I hope to be able to do for these FRIB experiments, is to tell you the deep fundamental nature of what's going on, so that we can see some of these hidden effects that way we might not really realize is there, but it is actually in the data.
Okay. We have a fun question for you from Crystal. Mm-hmm. She said, you might have to research and think on it, but I'm curious if you or your colleagues have a theory regarding how the Ghostbusters proton pack might work if it was real. How do you like that question?
Yeah, well, there's all so yeah, I'm trying to think back to the movie exactly what they said about it, but But yeah, there's all sorts of things you can do with elementary particles. So maybe I'll tell you some of the spin-offs that people can do in real life that are not part of a movie. So for example, there's lots of things you can do with nuclear isotopes to treat cancer just from the radiation, the localized radiation you get. For example, you can take a nuclear some nucleus that is unstable. So that means it shoots off a particle, okay? And then you can make that, for example, like iodine 131 is an example. And you can ingest that in some way, and you can have that because the iodine tends to be attracted to the thyroid. So if you have thyroid cancer. And so now this radioactive iodine can then target the cancer cells and just kill them because they're in close proximity to the cancer cells. So you can do all sorts of miraculous things, and you don't need to have science fiction to imagine these things.
Great answer.
Dean, you were talking about physicists earlier, and you mentioned theorists and experimentalists. Could you talk about the different approaches and what that means?
Yeah. It's actually a very, very different skill set. So obviously, both of us, we need to understand what's going on at the nuclear physics level. But a theorist is very often working at a computer to make a computational model of what's going on, or they're doing calculations of a simplified model using pen and paper to make equations that predict what's going on. So it's more mathematical or computational. And now experimentalists are typically, they first have to make the devices that will detect the particles. So a lot of the stuff that experimentalists work on are detectors, okay? So they detect various types of particles like photons. So you have gamma ray photon detectors, you have charged particle detectors. And so what's going on in an experiment is typically you accelerate these particles. So another part of the experiment is the acceleration process, but that typically requires some expertise and specialized expertise in building an accelerator, which is another aspect of nuclear science, what's called accelerator science, actually. Okay. So you accelerate these particles, and then you have a beam of particles, and then you have a target, and then that collision, and you have stuff coming out, and you try to channel the things you want to see, and then from the things you want to see, you then have a detector to try to detect what you hope to detect.
We have a question from Bob. What do you hope EFRIB will accomplish?
So what EFRIB, so there are actually some beautiful talks specifically on EFRIB. So if you haven't seen these talks by Zach Constant or Artemis Spiro, you should go back and look at the videos that they have. They'll tell you more about EFRIB. My talk was not so much about EFRIB, but I'll just tell you quickly that we would like to see a lot of these rare isotopes that we have never seen before. So what an isotope is you have a nucleus with a certain number of protons, okay, and a certain number of neutrons. An isotope is when you change the number of neutrons, okay? So you add more or you take away some. And so a lot of what EFRIB is doing is looking at these isotopes that typically have an exotic number of neutrons, more or neutrons or even maybe less than the number that you typically see. So they tend to be rather unstable or near the limits of stability. Now these nuclei actually are produced in astrophysical processes like we've seen a neutron star merger process from gravitational waves. And so we have indirect evidence that nuclei are being formed in this merger process. And so with EFRIB, we will actually, in the terrestrial experiments on land, on Earth, be able to produce a lot of these exotic isotopes that we believe are being produced in these neutron star mergers. And that tells us a lot about how the elements were created in our universe. So that's one of the big things for EFRIB. But I also mentioned the other questions, like what exactly are the limits of stability? How many, for example, if I have 20 protons, that's what's considered the element calcium. The question you might ask is, how many neutrons can I put on top of these 20 protons and have them all stick? And so we know the answer is that we can at least put 40 neutrons on top of this on top of these 20 protons. But the question is, how many more can we put on? And so that's what's called the limits of stability. But then there are other questions like whether there's some physics beyond the standard model of particle physics, and that by making these special nuclei that amplify the signals of this new physics, we can look for these fundamental forces that maybe we did not know, fundamental new physics that we did not know existed.
Well, we have just a couple minutes left. So everyone who's viewing, thank you again for joining us. If you have any questions, we can probably take one or two more questions. Dean, while we wait for questions to come in, could you tell us a little bit about what inspired you to take this career path and what your background is a little bit more, how you got to this point?
Mm-hmm. Well, I actually started off, well, I guess I should maybe start from the beginning. So when I was very young, I was interested in math. Always found that fascinating. And then I learned that physics used a lot of the most interesting math that I was learning. But then it would actually, you could make predictions about what's seen in experiments. So that was kind of exciting to me. So I got hooked on physics that way. Now, in terms of the type of research I'm doing now, I actually got into nuclear physics in kind of a roundabout fashion. I was always interested in being able to calculate something using a new technique. So I always had sort of this dream that you figure out a new way of calculating something, and then once you have this new method, you can then calculate a bunch of new things that had never been done before. So I got interested in using certain techniques like you've seen in my lecture today, but I didn't actually know which problems to apply them to. And then I learned about nuclear physics sort of from the point of view of that the algorithms I was interested in would actually work for these systems. So I kind of came to nuclear physics because I had a tool that could perhaps solve this problem. And so then I learned more about nuclear physics that way. So it's kind of a backwards approach.
All right, well, it doesn't look like we have any new questions coming in. Again, if anyone has any questions, please feel free to enter those into the comment section. But before we wrap up here, is there anything else that you want to share? Any online resources that FRIB has? Where can people learn more if they're?
Sure. So if you want to contact me, just send me an email at LEED. So Dean Lee is my name. So LEED @frib.msu.edu. And I'd be happy to chat with you.
Great, wonderful. Well, thank you again for joining us. For everyone watching, thank you again. We have more programs coming up with the MSU Science Festival. So keep your eyes on our Facebook page to learn more. Oh, one last question.
Sure.
From Crystal. Is teleportation of physical objects like people or non-life objects a reality for the future?
So sometimes when people talk about teleportation or quantum teleportation, they're not actually, it's not like in Star Trek where they have a teleporter and the actual atoms get moved from one location to another. That we don't know how to do that at all. But there is this notion of quantum teleportation where some information about, let's say, the spins of some system are encoded in a different atom located some other place. In other words, you know what you have here, and then you can transfer the information to another site and then have it go to the same configuration. That's what's called a quantum teleportation. So there's research on that.
Great. Well, there you go. Well, thanks again, Dr. Lee, and thanks again, everyone, for joining us today. Hope to see you again soon.
Thank you. Thanks so much.